Honorable Chairman, distinguished guests, and a special mention to my friend Klaus Thiessen. We are here to honor Karl Böer, a great physicist, a true pioneer in solar energy, and a wonderful friend and human being. I'm sorry I'm not with you. I mean, I would have given much to be there, but it's just impossible. And I feel, though, that I am there, and that's how I'm going to be talking. Why did I pick the title, How Will Photovoltaics Become Competitive to Fossil Fuels? I picked that title because it's an absolute necessity that fossil fuels, which are the cause of pollution, the cause of climate change, the cause of wars over oil, because of its geographic, dangerous, you know, where it's at, where oil is at, there's much trouble. Solar energy, I needn't tell this audience, has started really a new era for our world economy. And energy is the true basis for our world economy. What we do with the sun is we go back to really unplugging from the Earth's trees, its oil, its coal, and we plug into something that was born really in the Big Bang. We plug into hydrogen energy because it is the burning of hydrogen, the fusion, which gives us the photons, of course, to get photovoltaics. Conventional crystalline materials take years to be paid back in terms of energy. Their debt is very high, and it has many other problems. For example, it is quite thick, 500 microns thick. They are heavy and breakable. They suffer from cyclical shortages. In many cases, they require roof modification. And the production processes do not lend themselves to the kind of statement that we need to say we are going to be competitive, not to anything but fossil fuels, because that is the trillions of dollars worth of markets, and that's what will make a great change in our society, greater than anything for practically 1.5 million years when hominids began the use of fossil fuels. Now, the chance of being competitive to fossil fuels, I believe, are not very high for crystalline materials. But photovoltaics that are made from amorphous materials, that have multi-junctions, that can take the whole spectrum of the sun, 0.5 micron thick materials with the layers in it for the triple junction as small as 100 angstroms or less. And volume production 7 days a week, 24 hours a day, as I will show you, is a technology that I've developed with my colleagues, and the technology that I'd like to talk to you about today, because it will be competitive to fossil fuels. In the first slide, you see something that may be startling to you. What is a cardboard box doing in a discussion on solar energy? First of all, in that cardboard box, you'll see that it is holding 3,672 watts, that it is a relatively small cardboard box. And in it is a complete house in the sense that you have the energy in that photovoltaics that's in a row that gives you something that you can't have anywhere else. And I use that as a motif of my talk, because when you see cardboard, which is one of the most trivial in sense of all the containers one can put something in, and certainly the cheapest, you see that it is in a roll. You cannot roll up crystalline material. The cost of shipping that is very, very, very low. What I mean to say is that if you're sleeping on the floor, you can't fall out of bed. What I would like to discuss here then is how we can have technology that is really going to be and is in the process of being competitive with fossil fuels. I wanted to start with this Shell report to their stockholders of 2001, because they were, I think they've dropped out, the manufacturers of the conventional type of crystalline semiconductors for photovoltaics. And as you can see, they're heavy, they're ugly, and I think that the conclusion that Shell made is a good one. The thin film solar, which offers a wider range of applications than competing solar products, and is seen as the solar technology of the future. When I said ugly, here's what I mean. This is our photovoltaics mirroring, so to speak, a river that is nearby, a Thiessen-Krupp, and it's beautiful. It's aesthetically pleasing, and it's thin film organic photovoltaics. Technology, invention, new science are things that are not just in the future for photovoltaics, but they are progressing very rapidly. And we are so happy to being able to say and make our contribution to prove that by making photovoltaics the lowest possible cost, making them readily available throughout the world, you are creating a situation of great, even more than historical proportions. I'm going to briefly show these installations because it shows a special value of being flexible, thin, very lightweight, and beautiful. And by the way, in this particular application, the roof is charging our Ovonic nickel metal hydride batteries. Again, the ease of application is obviously seen to the left, where you see how they are installing the photovoltaic roofing that's on the Beijing Museum. It's beautiful, but it's also a low-cost way of installing photovoltaics. I just wanted to show you a shingle application. And of course, the big industrial and buildings, the large, what they call large box. This certainly is a good indication of the aesthetic value and the ability to put on photovoltaics in a manner that is very low cost. Now I'd like to come to what is the important part of our talk. You've seen the output, you've seen the products. This is a view of our 30 megawatt machine, and it is running at that point. You don't see any people because it runs continuously 7 days a week, 24 hours a day. And I'd like to start with what makes this the technology that it has to be on such an industrial scale, low cost, continuous web, triple junction, no stop and start. I think many of you are familiar with the triple junction. I just show it. It looks very thick and very big, but as I said, it's a half a micron with 9 layers of active materials, absorbing the spectrum of the sun that's available. Why do I focus on this? Because crystalline materials are made with 1 band gap. And here you see 3 band gaps. And even though it is a lower, quote, efficient material as of now, it is not the efficiency that you pay for. You pay for what you plug into the wall and get as watts. And the fact that the integrated energy of that in 24 hours, a day, week, a month, a year, gives you up to 30% more actual energy, watts, than you would get from the highest efficient crystalline material. So it is higher energy, higher output, and the inside of it is simplicity itself, where it costs billions of dollars to have a crystalline silicon plant for semiconductors. Here are the robotics and the clean room, of course, are their biggest expense. Our robotics is just like a camera, just a roll that goes through the machine and unroll. Its clean room is the machine itself. And the secret then to having a low-cost machine beneath that's not even $100 million against billions of dollars for crystalline silicon is of course a great advantage. That's 9 miles in a single run. And what you get out of it is someone is there looking at one of our people, looking at a roll, and what you're looking at is we load automatically 6 rolls, 3 rolls on each side vertically of the machine, and they're automatically installed in those chambers and fed through the photovoltaic machine. The means of making photovoltaics competitive to fossil fuel lies in that type of a machine that I've shown you, our Ovonic processor, because what it does, it can be, that is so important, it is a platform where if you can increase the throughput, you can have in the same floor space, you can have a 100 megawatt machine, not a 30 megawatt machine. If you increase its efficiency, you can have efficiencies that are even higher than the efficiencies of a crystalline material are available to you in our materials. Therefore, when you make a solar cell, you make photovoltaics in the manner that I've just described, you are making a new world, because that new world is a world where science and technology is changing the world for the better by solving serious societal problems, that which Iris and I have been trying to do and have been accomplishing since 1960. This overhead shows the internal, our machine being put together, so to speak, in that building, which is just a quarter of a mile from our mother photovoltaic plant. Iris and I are standing there with great pride, for we know that this process will continue and continue and continue. What are we doing to carry on to achieve our purpose? We are building new plants as we speak. There's one that is about a quarter of a mile from our mother plant, photovoltaic mother plant. There is 2 more being in the process of being built. There are many more that are being built. We have space and a new city that we're going to be placing probably about 12 more processors. I hold in my hands our ultralight material that we've had for these many years, and it has the same number of layers of active material. It has a 1/2 micron active film, and yet it is so light in weight that it is used for launchings that save a tremendous amount of money if you're going into space or dirigibles or what have you. But more than that, it has many territorial uses. A roll of this can be used to break apart water, because remember, our triple junction has more than enough voltage and current to inherently break apart water. With a couple electrodes in the water, you just bubble out hydrogen and you bubble out oxygen. That young lady is walking up a mountain that even a donkey can't go up. She's carrying our photovoltaics up to electrify her village. She's barefooted. She has the future on her back and the future in front of her. I want it to be that we just continuously make these processors, continuously all over the world, set them up, and continuously be in the process of replacing fossil fuels. And this is the way we can do it. Thank you.